Hello, everyone. Thank you for coming to my talk today about diagnosing colorectal polyps in the wild with Capsule Networks. This work that I'm sharing was accepted for publication at ISBI 2020 and is shared with my co-authors, Dr. Kandel, Spampinato, Wallace, and Bagci. So colorectal cancer is a leading cause of cancer-related death in the world. The lifetime risk of developing colorectal cancer is around 1 in 23 in the United States, and it accounts for roughly 10% of all cancer cases across genders. Now, in recent years, there have been a number of studies trying to create automated diagnosis systems for colorectal cancer. And a number of these studies, especially in the last few years using deep learning-based techniques, have been able to achieve pretty remarkable accuracies, above 90% even in some cases, which tends to be the clinical threshold cutoff. Is about 90% accuracy is where we want to see these systems before we start considering clinical usage. One thing I want to emphasize, though, is that these recent studies have all been on very controlled academic data sets, and they're quite unrealistic when compared to actual clinical settings. And I'm hopefully going to try to convince you of that in the next couple slides. So we can see here on the left is one of these sort of controlled academic data set examples. You can see here, this is a video, roughly 30 seconds long, of a polyp, very nicely close up. And if we look on the right, we can see this is an example of our in the wild data set, where we're given only a single image, and the polyp is very hard to even detect, let alone diagnose. You can see it here now marked with the red arrow. If we look at another example, here, this is using white light instead of the narrowband imaging that you saw in the previous. And again, nice video, multiple angles, zoomed in very close and centered on the polyp. And here's an example at right. You have our in the wild data set. Many of you probably can't even see where this is. We have a red arrow. You can see there on the wall where the polyp is located. One more example you can see over here. And this sort of gives you an idea of the difficulty of a more realistic clinical setting as opposed to the more academic controlled data sets. And we'll kind of run through this a little bit more in detail. On the left, this is an example of a typical data set. We can see it's limited in the number of polyps, typically less than 100. Up close video, 30 seconds, over 800 frames. And we typically get multiple viewing angles, multiple modalities, focus modes, lighting conditions. And all of these are able to provide nice complementary information for providing the diagnosis for a single polyp, right? So all of this information coming together to diagnose a single polyp versus a more standard clinical setting in our quote in the wild data set. We have 963 polyps from over 550 patients. We only have a single image provided per imaging mode. And often we're only even given a single imaging mode, so only white light or only narrowband imaging. And there's a large degree of interpolyp variation, whether that's scale or skew or illumination. And all of these make it extremely challenging to create a computer-aided diagnosis system where we are robust to all of these different variances in the images and given only a single chance to diagnose it correctly. This is our proposed solution that we have in this work. We decided to pursue a capsule network for trying to solve this difficult problem. Capsule networks are a new class of neural network that was popularized by Sarah Sabur, Nicholas Frost, and Jeffrey Hinton in 2017. The reason we're pursuing this is because they tend to generalize better with less training data. And a big reason for this is they are able to handle unseen variations in input poses very well. And this allows them to basically handle, given a single example of a polyp in like the bottom right, we can rotate that, top left, we can look at all different kinds of poses and still be able to generalize without having to see all the different variations that we could be given. And this helps us out a lot with this more realistic data set that we're working on. And lastly, we hypothesized that given these advantages, that in this difficult problem that a capsule network could possibly outperform a top convolutional neural network. The novelties we introduced in this work to accomplish our goal, we created a novel deep capsule architecture. We call it DCAPS, short for diagnosis capsules. This is partially based on the locally constrained routing technique that was introduced in TEM, which is the SEG-CAPS work. We introduced a new capsule-average pooling technique, or CAP. This allows us to perform classification on large image sizes. In previous works with the fully connected capsules, they were far too computationally expensive to be able to diagnose or run classification on large image sizes, rather than something more trivial like an MNIST or a SciFAR that deals with very small images. Next, we were able to improve results over the Inception v3 architecture, which was used by the current state-of-the-art approach, was a pre-trained Inception v3. And we reduced the number of parameters by as much as 95%. This is another advantage of capsule networks, is they're able to have similar predictive performance while using only a fraction of the model size of some of these top state-of-the-art CNNs. Lastly, in the paper, we provide extensive analysis of our results, stratified across polyp categories, scanner types, imaging modalities, and focus modes, because this is the first study on this much more challenging data, and we wanted to really provide a nice baseline and a benchmark for the field for future research in this area to be able to see the differences between these different stratifications of the data. This is our proposed architecture. This is DCAPS. You can see we take an input image, pass it through a 2D convolutional layer. After that, we form our first layer of capsules, and the rest of the network is a deep capsule network. So every layer, excluding the first, are all capsule layers. There's not just a single capsule stuck at the end. You can see in purple in the bottom right corner is the capsule-average pooling layer that we introduced. And then we use the length of the vectors to be able to give us our output diagnosis. And lastly, in the yellow, is the reconstruction of the input, the reconstruction regularization that Sarah Sabur introduced in her original work. And we'll talk about the results of that a little bit. So this is the capsule-average pooling that we introduced, one of the novelties of our work. The capsule-average pooling layer computes the spatial average of capsule activation vectors to reduce the dimensionality of features. And this works by having each capsule type compute an element-wise mean across the height and width dimensions of the capsule grid. In this way that we can preserve the length of the capsule vectors in each capsule type. And then finally, our final diagnosis is decided by the magnitude of the class vectors. So you can think of this somewhat analogous to a global average pooling in a convolutional neural network, but instead here we're computing spatial averages. We're using our capsule vectors instead of the scalars in CNNs. Next, I'll talk about the experiments that we conducted and the results of those experiments. The experiments were performed on the Mayo polyp data set collected at the Mayo Clinic Jacksonville by the citation number 9. In this study, there was 963 polyps from 552 patients, and the polyps were collected from standard and dual focus colonoscopes, where the dual focus mode contains both near and far focus modes from both white light and narrowband imaging settings. And we refer to these by the abbreviations shown below. We conducted 3 sets of experiments. Hyperplastic versus adenoma. This is one of the most common experiments that you'll see. Studies that include serrated, which is the next one, are very important because hyperplastic versus adenoma and serrated will be your leave in situ versus resect sort of classification. And because serrateds tend to be left out of a lot of studies because they're very difficult to differentiate from hyperplastic, we wanted to conduct another experiment that was hyperplastic versus serrated to see if we could differentiate these two. Here are the results shown using both DCAPS and the Inception v3 architecture. As we can see here, these 3 experiments are of increasing difficulty, and as we move up the difficulty scale, we can see DCAPS is outperforming Inception v3 by increasing margins as well. 17% for our first experiment, 27% for the second, and 43% for the most difficult, the hyperplastic versus serrated. Relative improvements in accuracy. We conducted several ablation studies for this work. One was on the number of routing iterations. We played around with the number of routing iterations, looking at 2 to 5 iterations at each capsule layer, and we found that 3 was the best, consistent with previous literature. We attempted to remove the reconstruction regularization to see what effect this actually has on the final results, to see if it is really contributing. And we found that the accuracy decreased on average by about 8% when we removed that. And lastly, a lot of these numbers are quite low, and we were concerned about what would happen if we looked at sort of a more ideal subset. We asked one of our physicians to select a subset of 100 images that were hand chosen to be sort of more ideal candidates, more realistic for the colonoscopist was able to actually identify the polyp and kind of zoom in on it a little bit better. It's a little more centered, a little bit nicer. And this we obtained an accuracy of 82%. So we can see that our method can perform better if the colonoscopist is able to localize the polyp region. So thank you for listening to my talk today. If you guys have any questions, you can reach out to me via the comments page or via email. Both of them are shown on the screen here. The project page can be gotten to via the QR code or the link provided. All of our code is publicly available for reproducing these experiments. And the code you can get to again from the project page. And again, thank you very much for listening to my talk. And if anyone has any questions, I can take those now.